So yeah, we're so it's going
all kinds of, it's some kind of weird. So now I'm on the trail to see if I can.
What was the like security like? Were you escorted to the cell When you came back, were you sitting I wonder if he was like interviewed kind of thing. Yeah. Exactly.
After 5 months. They just did it today.
Yes, it was just there about a minute ago.
Спектр нормально.
Yeah.
We're off by a sheet.
No idea.
Yeah, man, it was up. Yeah. So, unfortunately, we came out. My mom was there. Not the most specific to me, but it was definitely I worked here, I haven't lived here for many years.
That's so fun. Yeah. Very nice.
Before they start, can I ask you one question? Yes. Do you know if any TVs observed in the AGM? Type 1 agent.
Yeah, where I enriched was not the same.
I think we have a source.
Cool.
Yeah, we have a source where helium-2 broke light. Like there was like a prominent helium-2 4686. Really big, and it's in type 1 AGN, which is variability. The problem is that this period between when it's disappeared, when it's visible, and when it's disappeared, it's not covered by any domain service except let's see a quest. And let's see a quest is not public. I'm trying to get the right clip from there. I mean, like, I know somebody, but this person is just super busy. Yeah. So, but you don't know of any other cases? Because I just found, I tried to look for it.
It's like super low level activity.
Because I tried to, there, you know, you basically subtract off two spectra from SDSS. So you see like a continuum change because of the AGN continuum. And so there's clearly a broad line of helium-2, a little bit of helium-156, and narrow Balmer lines. I don't know why they're there. It's just narrow Balmer lines and no other narrow lines. So there's no narrow O3 or whatever. So it's just narrow Balmer lines and the broad helium-2. That's different than the spectrum.
That's different than anything I'm aware of.
Yeah. Okay. All right, because we recently took a spectrum just to double check that the helium didn't reappear.
Interesting.
I haven't looked at it yet, and we took the infrared spectrum 2 days ago with fire, so I'll take a look.
That's exciting. Yeah.
Cool. All right, so I'll talk to you later. Yeah.
There's lots of spots up there.
How will you possibly
Ja ping-pong как я не улучшил. Значит, я увидел, что там 25 происходит, но мне еще на неделе было нет. У меня просто вышли игрушки, получили разбили и пойдем стили.
Okay, folks, let's get started. I'm in charge today. So we'll have 4 speakers. Fabio Pacucci will get things off with a talk on breaking cosmic scales, unexpectedly massive black holes from JWST. Then Fabienne Nail, sorry if that's not pronounced right, on 3-dimensional simulations of exoplanetary atmosphere escape. Paola Dominguez Fernandez will talk about magnetic fields in galaxy clusters. And finally, Shelley Cheng will discuss estimating eruptive mass loss in massive stars with MESA. 10 minutes of talking, 5 minutes discussion.
All right.
Fabio.
Hi everyone. Thank you for being here. New venue, exciting. So do you all see here, or should I get?
No, it's good.
Okay. All right. So my talk today is about what JWST is telling us regarding the early evolution of black holes and galaxies. Well, we all know that on Earth, beauty is often regulated by proportions, but similar proportions sometimes are also seen in the sky. And it's been known for a long time that the mass of the black hole at the center of galaxies correlates with some properties of the host. And one such relation is the MM star that says that approximately the mass of the black hole is about 0.1% of the stellar mass of the host. Well, this is not always the case, and for example, several recent studies are suggesting that JWST data at high redshift is showing that black holes are very overmassive with respect to the stellar mass of their host. For example, in this recent paper with the Jade survey, they are showing that black holes are not 0.1% of the mass of the host, but more like 1% or 10% or even higher. While other relations, for example, the M sigma, the M dynamical, seem to be still valid. This is not the first time that this was predicted or suggested. Already about 20 years ago, there were several papers suggesting that the ratio between the black hole mass and the stellar mass should evolve with redshift. Already there were some sporadic observations in the previous JWST era, but now with JWST we are having an explosion of measurements of overmassive black holes at high redshift, higher than 4 typically. So there are two main questions here. So first of all, is this an observational bias? Of course, overmassive black holes are intrinsically easier to detect. And another very important question is, are the stellar masses in the galaxies actually well estimated? But why are we noticing this now in the redshift universe? Well, about 700 years ago, Dante and Virgil came out of the Inferno in the Divine Comedy. I'm sorry, I'm Italian after all. And they said that they can see once more the stars. Although in a slightly different way, JWST is also seeing the stars once more right now, because they're observing smaller supermassive black holes and the redshift universe. These are not giant quasars, they do not outshine the galaxy, so they can actually see the stellar component and see the stars and measure the stars again. So this is a study that came out about a couple of months ago now, and in which we have executed an accurate statistical analysis of the correlation between the supermassive black hole mass and the stellar mass between redshift 4 and 7. We consider observational biases and predict JWST observability of high redshift black holes, especially in the low mass range. This is the dataset that was available at that time. These are like 21 sources at the redshift between 4 and 7. And the supermassive black hole mass is estimated by broadline region H alpha. Stellar mass is available for all these sources. Here in blue you can see the local MM star relation. And these four horizontal lines here, they are the minimum black hole mass needed to execute at least a 3 sigma detection with the broad line region of the H alpha at redshift between 4 and 7. Now, we used an NCMC model that is basically with 3 ingredients: the local relation, which is used as a prior, the stellar mass function between redshift 4 and 7 to assign different weights to different galaxy sizes, and also the JWST H alpha limit between 4 and 7, like I mentioned before. All of this goes into the likelihood function, in which we included also a term that is a correction for the flux limited survey, what I was saying before. Overmassive black holes are intrinsically easier to see. All of this goes into the inference of the redshift relation, which we find to be this one in red. So in particular, we find a high redshift MM star relation that is very different from the local one. And in particular, the high redshift relation indicates black holes that are 10 to 100 times more massive than what is seen in the local universe, given a stellar mass, of course. So the standard intrinsic scatter is about 0.7 dex, which is larger than the one in the local relation. And we also conducted a statistical analysis for each stellar mass to show if the black hole mass estimated with the local relation and the redshift relation are compatible with each other. And it turns out that they are not. So they seem to indicate two different statistical populations. So I'm often asked, why the slope? Okay, the data points that you're showing here, they seem to be shallower with respect to the slope that is found at the end. Well, the MCMC code that we use is not a simple fitting, so we're not simply fitting the data, we're also taking into account other observational biases. One of the 2 or 3 reasons why the slope is actually steeper than what would appear from the data is that the code is taking into account that we are probably missing some data here, so it's assigning a lower intrinsic probability to the points that are here. So in this case, we actually find a slope of the redshift relation that is very similar, not exactly the same, to the one of the local relation. Since this paper came out, there were an additional 5, as far as I know, papers suggesting overmassive black holes at high redshift, so I updated the plot. And you can see that the redshift relation that we predicted still fits also new data very well. Now that we have a prediction for a high redshift MM-star relation, we can also make predictions on observability, right? So JWST strength is not only in expanding the redshift horizon, in seeing farther out, but also in allowing us to see smaller mass black holes. So in these plots, we show the expected surface density of black holes with a small mass, smaller than about 3 million solar masses, so the smallest approximately masses that are seen at this redshift right now, for the local relation and the high redshift relation on the right. Now, the inferred high redshift relation suggests that the small black holes are preferentially found in stellar masses of galaxies that are in log between 7.5 and 8, so much smaller than what the local relation would suggest. And this is actually quite in agreement with the data from the JADE survey, for example, in the paper by Maiolino, in which the smallest galaxies that are seen are approximately in that mass range. Also, our inferred high redshift relation yields a higher value of detectable black holes with a small mass compared to the local relation, with a boosting factor is about 5 at redshift 4 and even 18, so higher at redshift 6. We also studied the general mass distribution and not only small mass black holes. This figure displays the expected surface density of black holes with a mass lower than what is indicated in the x-axis, assuming the inferred redshift relation. And what you can see is that we expect many more sources that are detectable in current JWST surveys, or at least they are there, not necessarily detectable, compared to what was found, for example, by recent surveys. And we have yet to detect these sources because they may be inactive, suggesting a duty cycle between 1 and 10. The host may be outshining the AGN this time, or the AGN is obscured and not easily recognizable by line diagnostics. So in general, and I'm concluding, why are these high redshift galaxies so inefficient in forming stars? We're working on a simple model in which star formation in these high redshift galaxies is basically quenched once the supermassive black hole injects enough energy into the system to raise the temperature above the virial one. In practice, this turns out that if the ratio between black hole mass and stellar mass is higher than this value, which is calculated for this galaxy, for medium properties of these galaxies at high redshift, basically gas cooling is inefficient in creating the condition to further star formation. In fact, these galaxies that are found in JWST at redshift higher than 4, they are basically all in the quenched region, or some of them are transitioning to the active region, while local galaxies that are on the MM-star relation are mostly in the other region. So to conclude, this is a pictorial representation of the current black hole horizon that JWST allows us to see. The blue points here are the galaxies that we studied in this paper. This is the farthest spectroscopically detected black hole so far, GNZ11. So as you can see, these galaxies, the black holes, can be formed from a simple Eddington limit, or even slightly lower, accretion from light seeding in the very high redshift universe. So basically, JWST is allowing us not only to expand the redshift horizon to see farther and farther out, but also to study smaller mass black holes in the very high redshift universe. So I will just leave my summary here, and thank you for your attention.
Thanks, Fabio.
I wondering why you're expecting to see any relation at all, because if they're growing by accretion, you wouldn't expect any M relation. You would expect this if they grow by mergers.
No, you would expect it also via normal growth.
Normal growth for people that redshift 0 is mergers. That's the original, like the Cormindian hole. The linear relation is because the bulges grow the same way as black holes by mergers. So there you don't have any mergers. You grow black holes by accretion. So I mean I wouldn't expect. I'm really not surprised that you have big scatter, and I don't expect any relation at all if the growth is dominated by accretion.
Well, there should be some relation though, connecting the mass of the central black hole and how big the galaxy is. Also in the redshift universe, I don't see any particular reason. It's not just driven by accretion. It's not just driven by mergers in the local universe.
There's a question there, yeah.
Probably should know the answer to this, but do we have an estimate of the black hole stellar mass relation at redshift 2, for example?
So there are some estimates. The farthest estimate on overmassive black holes, they are about redshift 0.9. Okay, so mostly the Rhines and voluntary, those relations are very, very low redshift.
I'm wondering if we have any idea of whether it's kind of a gradual change.
So yeah, so the paper that I mentioned before, the one 20 years ago, they were suggesting a gradual increase of the black hole mass over stellar mass. And there are some papers, I think, that estimate, for example, these are voluntarian Rhines this time, so that they are opposite. This is 2016, I think, in which they estimate the MM star relation at slightly higher redshift, but we're still probably 1, something like that, so not as far.
Yeah, Tony.
So I'm working on a project where we're looking at a lot of clusters of galaxies, and we find high redshift galaxies that have been lensed by the cluster. So it's another way of finding very high redshift objects that are perhaps fairly small. And in a few cases, some of these distant galaxies seem to be fairly massive, but nevertheless have no central AGN whatsoever.
Okay.
And one of the problems with this program is that it's very hard to get time to get observations showing that there's no AGN.
Yeah.
Right, you apply to Chandra and say, we want to look at a galaxy that we think has no X-ray flux.
Yeah.
It's a little hard to get that through the referees, but and we're a bit puzzled by all this. But there do seem to be a lot of fairly bright, fairly high redshift galaxies that have no AGNs whatsoever.
Yes, and there is a big problem in actually detecting the AGN. For example, in Cheers, there is a lot of AGN, the little red dots, they have some broad line regions, but they are cross-matching them with X-ray data, like Chandra and whatever is available, and they are not finding any cross-match. So apparently, the presence of a broad line region, maybe, well, if they are heavily obscured, you shouldn't even see the broad line region. So it's very pathful. I'm not sure that X-rays really trace this particular growth. Well, we can talk about that. Yes.
Okay, thanks Fabio again. Fabio, we have Fabienne.
Kind of related, yeah.
Yes.
Okay, so hi everyone. Actually meet us later. So I'm Fabienne, and I'm a PhD student at the University of Amsterdam. And my supervisor is Antonia Oklapcic, and she was at the CFA before, so hi to everyone who knows her. And I'm visiting the CFA right now for 6 weeks, and I'm working together with Morgan McLeod on a very interesting project I will talk about in this talk. And I used AI-generated images just to make it a little bit more fun, so I just asked DALL-E, please make a Van Gogh-style atmospheric escape. So I hope you enjoy it. And yeah, first of all, why is atmosphere escape interesting? Oh, that's too far. So there are many reasons, but just to emphasize one of them. If you have a look at exoplanet demographics, here we see exoplanet mass versus period diagram. And you can see that there is a desert of intermediate mass planets. And we think that one mechanism, or like the underlying reason for that is atmosphere escape. So maybe a planet started out here, loses tons of its mass through atmospheric escape, and then actually moves down in this diagram. And I'm talking about hydrodynamic escape. So the Earth atmosphere is losing about 3 kilograms per second, so that's very little. But like a hot Jupiter atmosphere is losing 10,000s of tons per second. So that's a huge difference. And how do we observe atmosphere escape? When a planet is transiting like this, part of the stellar light is absorbed in its atmosphere or in its outflow. And we found, or it was found, that metastable helium is actually a very good tracer of this escape. And just to show you some observations of helium escape, we see the helium-9 here. It's actually a triplet, but we mostly focus on this component. This is an example of HD189, 73.3b. And you can see we have a large mid-transit absorption, and then also a little bit of ingress and egress absorption. So egress means the planet is just moving away from the stellar disk. And you can see that the egress absorption is slightly higher than the ingress, meaning that we have something like a comet-like tail. And that's what we're assuming so far, that the outflow is actually blown away by the stellar wind, forming a trailing tail. However, this year there was a publication of HET P67, and it's the opposite. So that's so interesting. So the planet is moving in this direction, and along the orbital movement, only a leading arm of outflow forms. So that is one question I want to answer while I'm here, or while we're working on this project. And there's another significant difference. In this case, the outflow is only a few planetary radii extended. But in this case, you see here's the orbital phase, so you have a high pre-transit absorption. It's filling almost half of the orbit, so it's like hundreds of planetary radii that this outflow fills. And yeah, how do we approach this? We are doing three-dimensional hydrodynamic simulations using the MHT code Athena++, but we only use the HT part. It's actually not MHT. And something I want to emphasize here, it's not self-consistent, the wind launching is not self-consistent. So we don't say we have this amount X of installation and this is causing this amount X of planetary mass loss. We parameterize the wind launching, and this allows us to cover a broad range of parameters and to fit observations pretty well. And then we use one of these snapshots, so here's the planet and here's the star. We use one of these snapshots and apply a radiative transfer to get the helium spectra out of it. And just on a side note, so this is a Van Gogh-inspired sun. We think that gas giants are likely tidally locked, so that one side is always facing the star. That's why the star is a little bit bored, so always on the same side. And yeah, so we implemented this in the simulation because we think the day side is much hotter, so the outflow should predominantly happen at the day side, not at the night side. So let's talk about this very interesting case of head P67. So the planet is moving in this direction, and during pre-transit here, so when it's not transiting yet, we can see these large absorption depth as an inflated hot Saturn, and the stars actually evolve, so there's a high installation. And the question is, what makes this leading tail? We tried several models to fit this observation. We started with an isotropic outflow, so day and night side outflow equally, and a quite hot wind. So this is what we expected so far. And if you use these parameter set, you get like a bubble-shaped outflow around the planet. Then we were turning anisotropy on, so that the outflow is predominantly happening on the day side, but still, like pre and post transit absorption is almost equal. And these contours, by the way, show the optical depth of the helium line, so you can see where the line is forming. And then we tried a cold wind of the planet together with an anisotropic outflow. And this matches the observation quite well. So here you can see we have a extended leading tail. So that's what we need, cold wind and a dominant day-side outflow. There is another complication, which is the stellar wind. So both winds are interacting. So we tried different stellar wind strengths. Here you see a weak stellar wind. The leading arm can extend widely. And then if the stellar wind is too strong, the planetary wind is confined. So this is also not matching the observation because the leading arm is not extended enough. And if you have a look at the light curve, so equivalent width of the helium line versus phase, the crosses here show the observational data. Just by eye, you could say, okay, weak stellar wind and intermediate stellar wind, these two lines match the observation quite well. However, it's not that simple. There is a but. If we look at the velocity shift of the line, which we can see here, so on the x-axis velocity shift, blue shifted, meaning the material is moving towards you as observers, and red away from you. And here you see the data points and the orbital phase. So this axis and this y-axis is actually the same. And you see during pre-transit, there is this banding happening of blue shift. And during post-transit, you see a very strong banding of blue shift. So we think what is going on here. Let's pretend I'm the planet, and this is my strong leading arm. I'm going that way. It's very hard to push my strong arm. So it's slightly pushed, but this is causing only a slight blue shift towards the observer. On the other hand, the weak T-Rex arm that's behind me is relatively easy pushed away, reaching higher velocities. So this is why this banding angle, let's say in this diagram, is higher. Okay, so if I fit now the weak stellar wind model, which looks pretty good here, you can see it's not matching the observational data well. It's actually one straight line, slightly blue shifted. However, the intermediate stellar wind model matches the observation a little bit better. You can see the bending is happening here, and then a stronger bending happening here. It's not perfect yet, work in progress. I would love your input. But yeah, this is my summary. In case you have any questions, please contact me, and my office is at P231, so please drop by. And thank you very much.
Yeah, there you go.
What spectral resolution did you have in your data? Because this 20 kilometers per second, you didn't show the error bars. So what is?
You're right. So the resolution of the of this measurement was 55,000.
Okay.
And yeah, I think this is approximately the resolution we need to make this analysis. You need to resolve like at least say 5 kilometers per second to see this difference here. Yeah.
So do you understand why your cold wind produces such a strong leading arm?
Yeah.
What's the physics of that?
Okay, so the material is overcoming the Roche law of the planet, so it's no longer gravitationally bound to the planet. And then it's like tidal forces, and it's dragged in a Keplerian shear. So there's a higher density compared to the hot wind where we have this bubbly outflow.
Yeah, but I still don't understand why the leading guy should be stronger than the trailing
That's
side.
because of the day-night anisotropy. So only if I include in a simulation that I have a day-night side difference, I get this leading arm. There's another observation of HAT-P 32b where we see both, very prominent and long leading and trailing arms. And we get the same with our simulations if we choose an isotropic planetary wind.
That is interesting. Okay, so by day side, it's on closer to the star, right?
Yeah.
In this picture, and
Yeah.
that is why it gets sheared forward.
Exactly.
Right, and the stuff that might have come in the back would have been sheared backward, but you don't have a wind there.
Yeah.
That's the idea. Thank you. That's very nice. Yeah. Are there other questions? Yeah, please.
Can magnetic fields be important for
Oh, that's such a good question. Like, I always ask myself that, because if you have a magnetically controlled outflow, let's say it's a dipole, I would think that the outflow is predominantly happening through the poles. So you have a completely different outflow configuration. And there's research on that, and they found that a magnetic field could induce the redshift of the helium line. So it's actually a very interesting question. But I think what we see in this observation matches pretty well this configuration of magnetic fields.
and other like this planetary outflows expected to carry magnetic fields too, or from the planets?
You mean if the outflows can? Honestly, I don't know. Probably. Interesting question, yeah? Yes,
Yeah, Josh.
What launches a cold wind?
Yeah, so we don't really know what is launching it. So if the heat is coming from inside the planet or if it's the X-ray reflux from the star that is heating it. But let's say we have a cold wind, it's and the planet is quite puffy, so low surface gravity. It only needs a tiny bit to overcome the potential to escape the planet. And then while it's expanding, it's cooling, so it's not heating anymore. So that's why we think it's a cold wind.
Okay. Thank you, Fabienne. Paola Dominguez Fernandez will tell us about magnetic fields.
I got better stay on this side. Yeah, so my name is Paola Dominguez Fernandez, and today we're going to be overviewing the topic of magnetic fields in galaxy clusters. The most direct evidence that we have of the presence of magnetic fields in galaxy clusters comes from radio observations. So here you can see some examples of the spectacular megaparsec radio diffuse emission that is not uniquely associated to radio galaxies, but is mainly associated to what we call the intracluster medium, or ICM. Now, we tend to divide this radio diffuse emission into classes. On one hand, we have what we call radio relics that are associated with merger shocks. And on the other hand, we have what we call radio halos located more at the center of clusters and more related to the turbulence of the ICM. Now, apart from this radio diffuse emission, we can also get information about magnetic fields from Faraday rotation studies, where by measuring the rotation in the polarization of the radio waves coming from a background source or a source that could be also embedded into the cluster, then we can infer things such as the strength of the magnetic field or the distribution of these magnetic fields in galaxy clusters. So one usual way to do this is to to get the electron number density from X-ray observations, and then you make an assumption on the magnetic field power spectrum. And with that, what usually is done is that observers would assume a simple power law, and with that they will get that the strength of magnetic fields in galaxy clusters is of the order of microgauss values, and that relevant coherence scales range from tens to hundreds of kiloparsecs. Now, in order for us to understand these microgauss values, we need to think about a seed and an amplification mechanism. An obvious option comes from adiabatic compression. Nevertheless, here, if we take typical values for a seed field, so for example, we can take magnetic field strengths inferred from cosmic voids, we would see that this mechanism is not efficient enough to explain the magnetization in galaxy clusters. Another more appealing option comes from turbulence and the so-called small-scale dynamo. So here, by the assumption of flux freezing, you will have that random stretching of your magnetic field lines due to turbulent motions can lead to the amplification of the magnetic field. And that idea can be seen in this plot here, where you see the energy power spectrum. So here, under this theory, you would expect that if you have a seed field, its magnetic power will start to increase, but also it will start to shift towards larger values. Now, when we talk about seed magnetic fields, we can think about forces within galaxy clusters expelling magnetic fields. We can also think about seed magnetic fields originated in the very early universe during inflation or phase transitions. We can also think about batteries that are seeding these magnetic fields through large-scale structural formation. Now, focusing on the primordial magnetogenesis scenario, what we did here is that we studied a uniform primordial seed field in cosmological MHD simulations of galaxy clusters. And we showed that by resolving a large enough dynamic range, one can actually see the action of these small-scale dynamo, and one can actually reach microgauss values at the center of galaxy clusters. Now, each of these turbulent magnetic amplification was seen in every cluster within a fairly small sample of 10 to the 15 solar masses, simulated galaxy clusters with different dynamical states. One thing that we observed is that the magnetic power is correlated with the mass of the cluster. So if you take a look to this plot here that is showing us the radio power observed of radio halos with mass, this will tell us, or kind of like support the idea, that these radio halos are being powered by the reacceleration of cosmic ray electrons by turbulence. Now, of course, here I am missing a lot of details on the sides of particle acceleration mechanisms. Now, another thing is that all these clusters show different final scales at which equipartition between kinetic and magnetic energy is reached. In particular, relaxed clusters tend to reach equipartition at larger scales than, for example, merging or post-merger clusters. So this led to the idea that we could maybe find a relation between the magnetic field growth and the merger history of the cluster. Nevertheless, this turned out to be a hard task, not only because of our low statistics, but because when a galaxy cluster is forming, there are multiple merger events, multiple injection scales, multiple turbulent cascades happening at the same time. And more into detail, when you are having an efficient enough turbulent magnetic amplification, then your magnetic energy can the magnetic power spectrum will be acquiring a certain shape that is very similar to the outcome from this small-scale dynamo theory. And once this happens, it means that the magnetic field is getting like strong enough. And in all of these clusters, basically this shape, although the amplitude and certain things will be changing, the overall shape wouldn't change till redshift 0. And so basically that is the reason why it was really hard to extract any information from a previous merger event. Now there's a lot of ongoing effort to try to study magnetic fields in the IGM. And one of those efforts is related to RM studies. And some of these observational data is starting to suggest that the primordial uniform magnetic field scenario would be ruled out. And if we think actually on the side of particle physics, from theory, it's actually really difficult to generate an initial magnetic field that would be purely uniform and homogeneous. And so actually there are various theories suggesting that if a magnetic field was generated in the early universe, it should be stochastic. And there are many details and many models around, but the general idea is that if a seed field was generated during inflation or during phase transitions, then there will be specific characteristics that will be reflected in the initial magnetic power spectrum of these seeds. And so, in principle, one could be able to distinguish these scenarios. Now, of course, this is a thing that would be better studied in other regions of the cosmic web, such as filaments or cosmic voids. Nevertheless, in terms of galaxy clusters, we wanted to know if placing initial stochastic conditions will still lead to micro-Gauss values in galaxy clusters. So we did one small experiment. So here a PhD student resimulated a low mass galaxy cluster with different initial stochastic conditions. And what she found out is that it is only in the inflationary scenarios that you can again recover these micro-Gauss values at the center of galaxy clusters. Now, if you focus here in these two RM maps of the same cluster with uniform and stochastic initial conditions, you would clearly see that there are only RM differences if we start to go towards the outskirts of the cluster. Of course, in these regions, the magnetic field is less processed by this small-scale dynamo amplification. And indeed, if we start to go towards the outskirts of galaxy clusters, and maybe we start to tackle filaments, we can start to understand different seeding scenarios. And so if you have strong and diffuse background sources, we can start to constrain the magnetization of these filaments. So one thing that one could do is compare the observed RM to that of a control field, or basically an RM value reference that you already kind of know. And with that, you could constrain the RM of filaments. And with that, you can get some information about cosmic magnetism. And so here, I think I'm a bit running out of time. So I will just finish with, saying that these type of studies are right now a really strong tool, and this community is starting to put a lot of effort in these type of studies. And actually, it's the aim of various polarization surveys. And so with that, I just want to leave you with just two very simple takeaway messages. And I want to conclude by showing you this diagram that I like a lot about the intercluster medium. So here you can see all of the processes happening in the ICM. So today we just talked about gravitational energy, MHD turbulence dynamo, and seed magnetic fields. But if you want to understand more about this radio diffuse emission that I mentioned in the beginning, we also need to understand the part of cosmic ray physics and particle acceleration mechanisms in the ICM. So I've been working a bit with particle acceleration at shocks, and that's a topic that I presented recently in the high energy seminar, so I didn't want to repeat that here. But now I'm starting to explore new territory, so if you have some interest in any of these topics, so please just contact me, and I'm always open for new collaborations. Thank you.
Time for some questions. Yeah.
So I have a question on the previous slide. So how do you decompose the rotational measures for each component on those ratios? And then the following question is, what's the level of the RM filament compared to the other components?
Yeah, so that's a good question. So this plot here is from observations. This is from simulation. So he did one exercise. So we selected a control field that was basically nothing touching filaments or part of the cluster, and there we compute an RM like as a basis. Then we compute the RM from the filament itself, and then all of these components that you will have in practice in observations, we just assume certain RM distributions for these. So for example, the galactic noise that you will have, there are already some observations that can more or less predict how it is. So it's basically a normal distribution, and we know the sigma more or less, which is 6 radians per meter squared. And so with that, then we did just like a statistical analysis to try to tell, like, okay, we have the RM distributions from the filaments that we know, the RM distributions from the control fields, and then you want to test if these two distributions would come from the same parental distribution, right? And what was the second question?
So what's the level of RM filament compared to all the other components?
Yes, so in this work, this is the LOFAR survey. And so here they are having, so they plot the number of filaments that each of the sources that they detect are crossing.
So I had a question about, I mean, this is a small scale dynamo, right?
Mm-hmm.
That means what? Is it at the inner scale of the turbulence, smallest scale, or is it the grid scale? I mean, where is it happening in your simulations?
So here it's happening till basically till we reach equipartition. So from the simulation resolution until 50 to 200 kiloparsecs.
So that is not the grid scale. You are getting a range of scales.
Yeah. So you have to resolve enough in order to get it to start, from the resolution scales and then grow. On. Yeah.
Very good. Yeah. Thank you. Okay. Let's thank Paola. Shelley will tell us about massive stars.
Oh, yes. All right, is it working? Okay, good.
Hello.
So, hi everyone. I'm Shelley Cheng, and I'm a PhD student here at Harvard. My advisor is Charlie Conroy, and he's great to work with. And so this is my kind of thesis project now, and this is in collaboration with scientists at the CCA. That's why there's a Science Foundation logo at the top, and it's about massive stars and mass loss. So firstly, why do we care about massive stars? I'm going to start off with this very beautiful star. It's the nearest O-type star to our sun, Zeta Ophiuchi, and it has this beautiful bow shock kind of feature. This is because it travels very fast through a region of the galaxy with a lot of dust, right? So firstly, they're beautiful. That's one reason. However, more concretely, for everyone else in the room, in terms of galaxies, compact objects, and supernovae, massive stars are quite important. So firstly, for galaxies, massive stars can alter the density and overall movement of matter in galaxies. And quite obviously, there's stellar feedback and stellar winds. So that can play a huge role in the evolution and kind of behavior of galaxies. For compact objects and supernovae, massive stars are the precursors of these. So for example, for compact objects, if we understand the mass loss of these massive stars, we can better constrain the starting masses of compact objects, right? So, have those starting masses for the LIGO people to explore everything. And for supernovae, massive stars kind of can lead to supernovae, obviously. And there is a type of supernova called type 2p with pre-brightening phases before kind of the big luminosity feature, and those baryon phases are associated to mass loss of massive stars. So yeah, massive stars are important. Yeah. So one type of massive star we care about are red supergiants. So observationally, we can actually plot them on an HI diagram, so standard diagram, log luminosity, log temperature on a flipped scale due to historical reasons. I plot two evolutionary tracks. And so a famous example of a red supergiant is this beautiful Betelgeuse, which may or may not go supernova in the medium to far future. And one interesting feature about red supergiants is that observationally we haven't really seen them above 20 to 30 solar masses. So the reason behind this is not entirely clear. People have generally appealed to post-main sequence mass loss. However, the kind of theoretical underpinning for this lack of red supergiants is not that clear. So that's a mystery. Secondly, there's a type of massive star called luminous blue variables, LBVs for short, and these exhibit something else called eruptive mass loss. So this is an example, AG Coronae, and I want to emphasize this is a star. This is not a supernova. It's still a star in the middle, and it has this huge shell of material, right? And based on the kind of width of the shell and the integrated light of the shell, we've been able to kind of estimate a mass loss rate of 0.1 to up to a few solar masses per year. Obviously, that can't exist for longer than a certain number of years, otherwise the star will just dissipate. But there's a short-term kind of massive amount of mass loss. We call this eruptive mass loss. So on the diagram here, it's the same diagram as before, however now I show three empirical tracks. The two dotted green lines are just quiescent and outburst LBV, so ones that are losing mass and are not losing mass. And for the HD limit, the Humphrey-Davison limit, it is the kind of observational equivalent to the Eddington limit for stars. So yeah, those are just some empirical tracks. So far in the study of massive stars, there's been 3D simulations that kind of attempt to explain this eruptive mass loss or mass loss in general. And we focus on the left here. This is the gas density plot with like different coloring for different levels of gas density. One thing to note is that it's not really a spherically symmetric problem, right? So you see these big plumes in purple. You also see a lot of convection kind of happening and turbulence. Yeah, so it's a very complex system, not quite simple. And the biggest kind of conclusion from this study, this 2018 Nature study, is that helium opacity peaks in the atmosphere can drive mass loss. So these peaks occur when it's cold enough for helium to recombine, so around this purplish pink region. And that's kind of the main conclusion of the study. So this is very informative. Are we done? Not quite. And the reason for this is that these 3D simulations can only capture specific snapshots in time, so specific points on the HR diagram. And even 3 simulations, 3 points on the HR, cost over 15 million CPU hours. So that's not really realistic if you want to study a single star through time or multiple stars through time. So we need a simpler model. So this motivates our research questions of, can we actually understand eruptive mass loss in massive stars in one dimension? One dimension as in, I assume my star to be spherically symmetric, and I only care about like a single line of sight from the center to the surface. And secondly, can we estimate a mass loss rate for the massive stars and maybe compare with observations? So to do this, we're going to use MESA, so Modules for Experiments in Stellar Astrophysics. It's a great code. It solves all the stellar structure equations. It includes convection, macrophysics, and some additional physics. So great code. And we're going to focus on stars between 10 and 100 solar masses from solar metallicity and below. I'm going to show the solar metallicity models today. And before I delve into kind of the results and everything, I'm going to talk about the mass loss. There's 2 types of mass loss occurring at the same time. So of course, there's these continuous winds that occur throughout the evolution. It has lower mass loss rates. This is well understood. And then secondly, there's this eruptive mass loss, which is the new ingredient here, right? And this only occurs during parts of the evolution and has a higher mass loss rate. So for the first one, continuous winds, this is a pretty much well understood kind of problem. It's a line driving wind mechanism that's applied in the MESA code. It's called the Dutch wind because the authors are all from the Netherlands. And this m dot is dependent on metallicity, mass, luminosity, effective temperature. So it's a line-driving wind mechanism. A photon hits an ion. There's emission or scattering that occurs. Momentum is transferred, and then it collisionally couples and can drag the kind of photon out. So yeah, this is well understood. However, for the eruptive mass loss model, there's no kind of out-of-the-box implementation in MESA. and the kind of physical motivation of a model isn't really well established in literature. So we're going to do our own. In a star, energy is transported in two ways, so radiative diffusion and convection. So for the first one, radiative diffusion is kind of a random walk of a photon, and for convection, the photon is trapped in the bulk motion of fluid. So if we want mass loss, we ideally want to focus on radiative diffusion, so the photon has a chance of making it out of the star, right? So now I'm going to show this kind of plot. Let's walk through it. On the x is log T, so the surface is on the left and the core is on the right, higher temperature, lower temperature. And on the y, I have a ratio between a certain luminosity and the Eddington luminosity. The three different types of luminosity shown is the total, the radiative, which means that the luminosity carried by radiative diffusion, and the convective, right? And the black line is 1, so everything above the black line is locally super Eddington. And the red line here is a critical optical depth, which kind of defines regions where it's dominated by radiative diffusion or convection. So if we want mass loss, we want the star, the piece of mass in the star, to have a reason to want to leave, so locally super Eddington, and then it has to be shallow enough to actually be able to leave through radiative diffusion, right? So this is the region of this plot where we are looking at mass loss that's potentially occurring. So in equation form, the critical optical depth is C over V sound, so can a photon make it out? And I have this excess luminosity from everything that's super Eddington, that's radiative, and then I get a dynamical time, I pair that together, I have excess energy. I compare that excess energy at each radius, and see if it's greater than the binding energy. If it is, I assume that piece of mass gets kind of ejected at the dynamical time. And then again, I use the dynamical time again to account for the units, and then have a mass loss rate. This xi factor here is kind of a tuning factor, efficiency factor, or fudge factor. Yes. We expect that obviously to be less than 1, the fudge factor, because it's kind of natural to think that a piece of mass wouldn't just suddenly leave as soon as it's locally super Eddington, right? So this is an overestimation of the mass loss, and that's well understood, but that efficiency factor can be tuned with observations. Right, so just to see a bit more clearly how this two different types of mass loss occur at the same time, here I show a mass loss over time. This is the HI diagram. The same things are labeled in different colors. So eruptive mass loss and the wind mass loss in black. So we can see that, yes, the wind mass loss occurs throughout, and then the eruptive mass loss only occurs in a small region. So this kind of verifies the intention of these mass loss schemes. So before I show the results, I'm going to show the plot on which I will plot my results. So again, HR, and each track is a cell evolutionary track from main sequence all the way till the model crashes, basically. There's 3 evolutionary tracks, as I shown before, and I show every 5 incremental gap in mass. I did run every single increment in mass, but that would make the plot impossible. So yeah, that's the structure. So here are the preliminary results, right? So let's focus on the left here. This is at efficiency of 0.01, so 1%. And you can see here that I still get my red supergiants. However, here at 10% efficiency, I no longer get my red supergiants. I see a lack of red supergiants, which may reproduce that observational kind of fact. Also, the temperature at which all this mass loss occurs coincides with the helium hydrogen merged opacity peak. So that's also promising. And additionally, this is a recent 3D simulation, courtesy of CCA postdoc Jared Goldberg, and it may or may not match the theoretical prediction. So that's also promising. And overall, we can estimate it using 1D, and we actually can reproduce that qualitative missing red supergiant, and we can calibrate using efficiency factor. Thank you so much.
Thanks, Shelley. Yeah, you go.
There is an iconic case of eruptive mass loss, the Homunculus Nebula, the Eta Carina, and it's not spherical symmetric. So how do you think is important to, like what can be the factor you are underestimating or overestimating the effects if you go from 3D to 1D? Okay, so in a 3D, so the reason why 1D has limitations is because
things are trapped as a stack, right? In 3D, there's turbulence, there's convection, there's more dimension to move around. And ideally, if you want to get out, you can go around. There's no around in 1D, right? So that's the first thing. With Eta Carina, it's actually not symmetrical. And I was actually going to use that as my plot, and I was forced to change it by everyone telling me. And the reason behind that is that people think it could be due to a binary or triple, or there's multiple stars involved. And that's why it's not symmetric. So it's not just a singular star losing mass, which would be symmetric.
But all massive stars are multiple, no?
Yeah, but so it depends on how close it is and interactions like that. But it should be a spherically symmetric behavior. Yeah. More or less, yeah.
So Shelley, you have this fudge factor.
Yeah.
Sorry, efficiency factor.
Yes.
Sorry.
Fudge factor.
Right. And then you had one, honest to God 3D simulation.
Okay, so again, X and Y of this point, color of the point, all not sure right now. The 3D simulations is like preliminary and hand wavy, yeah.
But does the 3D simulation directly tell you what psi is? Or is this completely just a fitting parameter?
So the 3D, yeah, it's difficult. It can't directly tell you because in a 3D, again, there's other pathways.
Things can go out,
But you can get the predicted m dot from 3D and just divide and then get a xi. That's one way. However, I think the next follow-up project will be to use observational studies of LBVs as well as maybe supernovae data to actually constrain xi that way as well. Otherwise, we're not just relying on single data points of 3D simulations because there's only like 5 data points so far, right? And that's a little limiting. Yeah.
Okay, Morgan.
What's the opacity source on the hotter, like the bluer stars?
The what?
At high masses, yeah.
Yeah, so that's the iron opacity peak.
Oh, okay,
Yeah,
so
I
that's
think-
iron, and then on the right is helium?
Yeah, that should be, yeah.
Interesting.
That's not really dominant though. It's actually lower than the Dutch wind model. So let me show you.
And in both
So if you
of
can
these...
see here, that squiggly behavior is retained here. So this is the total mass loss now. But like over there, the Dutch wind exceeds whatever iron opacity peak wind occurs, yeah. So it's only dominant in this red supergiant kind of.
Okay,
Yeah.
Interesting. And then, is this what we would, does this show up in a 1D model as like a density inversion layer or something like that?
Yeah, it can.
Yeah, okay, okay.
Again, the MESA modeling is a little challenging numerically, so I can't really give conclusive reasoning about what exactly is happening, but yeah.
Okay.
Yeah.
Interesting.
So there are density convergence that causes, there's a lot of,
To balance the
Yes.
essentially super Eddington.
Yeah.
Okay.
Yeah. So the code tries to make it not super Eddington to survive.
Yeah.
But this method is kind of an alternative way to resolve the super Eddington problem when it evolves, because it can just eject the mass, get rid of the energy.
Yeah.
Very good. I think we've reached the end of our time. Thank you, everyone. Thank you, speakers. Nice stuff.
Thank you.
Just leave this here, right? Somebody will take care of it.
I think so. I think TJ and Declan are here.
Yeah, nobody.
This is one of their phones.
It's me, yeah.
Good job. Okay.